All right, you guys, we are going to dip into some probability for the week. Fundamental counting principles, the first thing we're going to look at. Essentially, it's a really fancy way of saying we're going to learn how to count different events. All right. So the first one we're looking at is the situation where we have shirts, pants, and shoes. All right. So we only have one pair of shoes. But we want to figure out the number of combinations that are actually possible. So we have a red, we have a green, we have a yellow shirt. So you're obviously going to pick one shirt. You have pants or shorts and a pair of shoes. All right. And that's kind of the sample space zoomed in so you can see. So we're going to pick one top, one shorts, and one shoes. A lot of times people will use a tree diagram to kind of denote things. So we're going to pick a pair of shoes. And then if we pick pants, we can pick a red shirt, a green shirt, or a yellow shirt. So there's three options there. If I pick my shorts, I can pick a red shirt, a green shirt, or a yellow shirt. This is what's called a tree diagram, you guys. Sometimes tree diagrams can be used to figure out the total number of combinations in a given sample space. So if we have one pair of shoes, we have two pairs of shorts or pants, two bottoms, if you will, and then three tops. All right, if you notice the total number of outcomes, we can have 1, 2, 3, 4, 5, 6 total outcomes is our answer. Okay. So the question is, do I really need to draw a tree diagram every time? And the answer to that is no. And that's what the fundamental counting principle says, you guys. All right. So if we are trying to determine the number of outcomes in a sample space, that can be found by just simply multiplying the two numbers of ways together, or the 3 or the 4 or the 5, whatever the number of events you are looking at. All right. So in this instance, if you look at what we had before, we had one pair of shoes. We have two pairs of bottoms, three tops. 1 times 2 times 3 is 6. So it does in fact work out. So that's what we're going to be doing for the first part of the day, and the first part of your assignment is all about counting just basic events like that. So we're going to kind of go down here looking at some different situations. So if we roll two standard dice, hopefully you guys know on a standard dice, looking over here, there are 6 outcomes on each dice. So if there's 6 outcomes on the first die and 6 outcomes on the second die, to get the total number of outcomes when we roll 2 dice, we multiply those events together. And if you look up or Google sample space of 2 dice, you'll find a million different pictures of the different rolls possible when you roll 2 dice. Okay, the game of craps, if you know anything about casinos or gambling, is based on rolling 2 dice and the outcome of those. Okay. Next situation, we're looking at a 10-question true-false practice quiz. So if we think about it, we have 10 questions, each with 2 outcomes. So there's 2 outcomes on the first, 2 outcomes on the second, 2 outcomes on the third. We're going to do this 10 times. In essence, we have 2 to the 10th. So the number of ways I can answer that 10-question true-false quiz, there is 1,024 ways. So basically meaning if you guess on a 10-question true-false quiz, the chances that you get 100% are very little. We'll talk about probability in a little bit. All right. Using that same mentality, we have a 25 multiple choice test final exam. If we were in class, this would actually be our final for the year, but you guys don't have to worry about that this year. So we're going to do a 25 question multiple choice test, A through D. So using that same mentality before, there's 4 outcomes on all of these questions. We're answering 25 times we wind up with 1.26 times 10 to the 15th. And with some of our counting, you guys we will need to use scientific notation, and that's perfectly a-okay. Just be mindful of that moving forward. You don't need to write down the 87 decimals you see in your calculator. Round off to the 10th, 100th, or 1000th and use scientific notation. That will make your life easier. All right. There's also going to be different situations where maybe we'll change the context of the problem with our counting. So looking at license plates, 6 characters are used, 3 letters followed by 3 numbers. So it says how many plates are possible if letters and numbers can be repeated. Well, looking at things, we have 3 letters followed by 3 numbers. And you have the glorious state of Minnesota there in the middle. So if we think about things, if they can be repeated, we have 26 letters to start. And I can repeat letters, so I'm going to have 26 outcomes each time, followed by 3 numbers. Well, digits range from 0 to 9, which is 10. And if numbers can be repeated, we have 10 times 10 times 10. The fundamental counting principle says we just multiply all of our events together to get the total number of outcomes in our sample space. So we get 17,576,000 total license plates are possible using those parameters. Okay. When we look at vanity plates, those are like these in the picture. Not my fave, in all honesty. When people put like, I'm awesome, or like loaded, or, I'm better than you on their plates, I think that's really, cool if you do that, but I'm not a fan of vanity plates. But vanity plates are a combination of letters and numbers. So we want to figure out, in this case, how many 5-character vanity plates are possible. When we think about the total number of events between letters and numbers, there's 36 different things you could put in there. So we're not worrying about special characters or anything at this point. It's just letters and numbers. So if we're looking at 5-character vanity plates, we're going to have 36 to the 5th, essentially, because we have 36 outcomes and 5 places to worry about. Again, the fundamental counting principle says we multiply everything together, and we are going to get 60,466,176 different 5-character vanity plates are possible. And that, you guys, is basic counting for the start of the unit. Continuing on, you guys, the next way we're going to learn about counting is what's called permutations. Permutations are specific orders of objects. So the order matters. So when we're thinking about a race, being first is not the same as being second. So that would be a permutation. If I was looking at toppings on a pizza, that the way I order it doesn't matter. If I say pepperoni sausage, sausage pepperoni, I'm going to get the same pizza in the end. So that's going to be a combination, and that's going to be the third way to count we're going to look at, okay? But bottom line, permutations are where order matters. So that's going to be kind of the key phrase today. So we count them really similarly using the fundamental counting principle. However, in this instance, if I have letters A, B, and C, and I want to put them in a specific order, once I use one of those 3 outcomes, I can't use it again, all right? Which means if I used A in my first spot, that means I only have B and C available in my second spot. And then just like before, we're going to multiply those together. So there are 6 different permutations of 3 objects. All right. So looking at things, this kind of brings us to our first, definition for permutations. And that's going to be the word factorial. all right? When you see an exclamation point in math, that means we start at n and we keep counting down until we get to 1, and we're going to multiply those all together. Okay, so a factorial can be used a lot of the time with permutations when we're counting, and a lot of you are going to figure out where that button is on your calculator. Okay, so let's start. How many ways can we arrange the first 5 letters of the alphabet? So if you think about this, we have 5 letters to start. Once I use A, I can't use it again, so there's only 4 letters for that second position. Then I only have 3 outcomes, then I only have 2 outcomes, then I only have 1 letter left that can be used. So if you want to shorten this up, instead of writing out 5, 4, 3, 2, 1 and multiplying all those together using the fundamental counting principle, you can just write 5. Just kidding. It's 5 with the factorial symbol. This is not an exclamation point, but these two mean the exact same thing. Okay, so if you actually can find the button on your calculator, it's under the math menu. You'd arrow over to probability, and then you'll find, I think it's either the third or fourth line down, you'll find the factorial key. So if you type in 5 factorial, you will wind up with 120, or you can just multiply out 5, 4, 3, 2, 1 by hand. Okay, looking at the Kentucky Derby, all right, there are 16 horses in the race. We're looking at first, second, and third. So really similar to the last question, but this time I don't care about all the order of the 16 finishers. I only care about first, second, and third. So there are 16 different horses that can finish first. If you have, one of the horses, we'll call him, Black Panther, if you will. He finishes first. That means Black Panther can't finish second. So there's only 15 horses that can finish second. And then we have, Velociraptor, who finishes in second. He can't finish in third. So there's only 4 outcomes that are left. So then we have 16 times 15 times 14, all right? If you do want to shorten this up, you could just, let's get the answer first, 3,360. Or we can use permutation notation. Since the order of the horses matters, we can start with 16 objects and understand that we're talking about permutation matters. The second number in your notation is going to be the number of spots you care about. So I start counting with 16 objects. I care about 3 positions. If you go into that math menu, arrow over to probability, you're going to find that permutation key. If you do 16 permutation with 3, you will get the exact same answer. Okay? It's important that you know, number 1, what your calculator's actually doing when you type that in. And that's what the formula is given here. And today, you're going to have a few opportunities to actually write things out. So when you see a factorial in your assignment, 7 factorial doesn't mean 7, all right? But we actually want you to write it out and show us what that actually means. So write it out and then give us your answer, okay? When we're looking at permutation notation, it's super important to write as well. Keep in mind, 10 is where we start counting. The second number is how far out we go. So you're welcome to write it like this according to the formula. Or you could shorten it up and just say 10, 9, 8, 7. And the reason I stopped at the 7 is I cared about 4 positions. Okay? And if you think about this, if I was to write out 10 factorial and I have 10 down to 1 on top, 10 minus 4 is 6. I'd have 6 down to 1 on the bottom. 6 down to 1 would cancel with 6 down to 1 on the top. So I'd be left with 10, 9, 8, 7 in the problem. Okay? When I'm using variable notation, things get a little bit more dicey. So this means I have n minus 2 factorial over n minus 2 minus 3 factorial. Okay? So essentially, we have n minus 2 down to 1 and this is n minus 5 down to 1. Okay? So keep in mind, if I use the mentality I had back here on this question, n minus 2 is where I started counting, and I care about 3 spots. So I want to get a number smaller than n minus 2, which is going to be n minus 3. Then I want one more position, which is going to be n minus 4. This is probably the hardest part for people to understand, because even though our numbers 2, 3, and 4 are getting bigger, the overall value of the number is actually getting smaller. Okay? So that's probably the most confusing part of the permutation aspect of the day. Okay? And good news, we don't have IQs, so we won't really delve into that too deeper than that. All right? The last permutation thing we're going to look at are repeated values. So when I spell waterfall, if I told you to close your eyes and I said I switched the A's around, would the word be different? The answer is no. Okay? So we're going to use distinguishable permutations when we have repeated instances. So if I look at this, there's 9 letters in the word waterfall. When I have repeated letters such as A and L, what we do normally, the number of permutations in the letters waterfall would just be 9 factorial. But since I have repeats, I need to take those into account. I have 2 A's and I have 2 L's. So what you do is you divide by the number of repeats, okay? And the reason is if I switch the A's or switch the L's, it doesn't change the appearance of the word, okay? In this instance with Mississippi, we have 11 letters total. So if I was just looking at straight up different permutations of those letters, it would be 11 factorial. However, there's 4 S's, there's 4 I's, and there's 2 P's. So when I switch around those letters, it doesn't actually change the word Mississippi. It's going to look the same. So we divide by the repeats again, which is 4 factorial. There's 4 S's, there's 4 I's, and there's 2 P's. Make sure when you type it in your calculator, if you have multiple values in your denominator, you use parentheses, and you'll wind up with 34,650 different permutations in that instance. The last method of counting we're going to look at and explore is combinations. Combinations are when order does not matter. And a lot of times, you guys, we're going to talk about decks of cards. So if you don't know a deck of cards, I would get to know it really fast. There are 52 cards. There are 4 different suits: clubs, spades, hearts, and diamonds. And there are 13 cards of each suit. 4 times 13 is 52. Keep in mind, face cards are your jack, queen, and kings. There are 12 overall. Otherwise, you have numbers essentially ace through 10 or 1 through 10 as well. Okay? So keep in mind the deck of cards, and I do post the sample space as well so you can kind of see things if you forget. Combinations are a little bit different than permutations, you guys, because order doesn't matter. So looking at example 1, 16 people are on a team, 2 are selected to be captain. Well, it doesn't matter if John or Sally's picked first, both of them are captains of the team. So the question is, how many ways can captains be chosen? Well, we have 16 people on the team, 2 are going to be chosen to be captains. In this instance, it's really kind of similar to that method of counting with permutations. So we have 16 people. Once I choose John, I can't choose him again. So there's 15 people in that second slot. Then what I do is I divide by the number of ways those 2 objects can be ordered, because again, order does not matter. When I multiply those out, I get 120 different ways. So keep in mind, essentially, it's our permutation divided by the order of, we'll say, our objects, if you will. And that's where this formula comes into play. You can see we start with our permutation formula, but then we're dividing out by the number of ways you can order those R objects you selected, okay? This is your formula expanded out. So you can see the n factorial over n minus r factorial is your permutation piece, but then we have the extra r factorial in our denominator because order of those objects does not matter. All right, so getting into things, looking at how many 5-card hands are possible using a standard deck of cards. Well, if I want to write this out, I know there's 52 cards in my deck. Since I'm looking at playing cards, I'm going to use combinations instead of permutations. All right. Keep in mind we're taking out 5 cards at a time, so I'm going to say 52. A lot of times the word we're going to say is choose with combinations. So I have 52 cards. I'm choosing 5 of them. You can either use the button on your calculator, or we know with our notation, 52 factorial over 52 minus 5 factorial divided by 5 factorial. This is going to work out to be 52, 51, 50, 49, 48, because we took 5 cards, but then we don't care about the order of those 5 cards, so we divide by 5, 4, 3, 2, 1. You wind up with 2,598,960 different hands of 5-card hands are possible using a standard deck of cards. If I want to look at part B, how many different 5-card hands are possible of the same suit, all right, we go from 52 cards down to 13 because there's 13 in each suit, correct? And then we get 1,287. So there are, looking at just hearts, 1,287. Looking at just clubs, 1,287 ways of getting a hand with the same suit. So what we want to do is to make sure we multiply this answer by 4, because there are 4 suits, to get the actual total, which is 5,148 different same suited hands. If you're a poker player, this is the number of flushes that are possible in the game of poker. Okay. The last question in this example, or this set, is looking at 3 kings and 2 queens. Well, these ones are really actually simple to think about because we have 4 kings in a deck. We want to pick 3 of them. There's 4 queens in the deck, and we want to pick 2 of them. If we think back to that first aspect with the fundamental counting principle, we always take our outcomes, or the number of ways an event can happen, and we multiply them together. So we just have 4 choose 3 times 4 choose 2. We can either use the formula above or use the program on our calculator that already has the formula pre-programmed in it, and we wind up with an answer of 24 different full houses with 3 kings and 2 queens are possible in a standard deck of cards. The last example we want to look at today, sorry it's been long-winded, but looking at just different combinations of ordering food. So when I'm looking at omelets, it doesn't matter which way I order the omelet, I'm still going to have the same omelet versus if I say peppers or onions, that's the same as onions and peppers. So how many different omelets can be formed with 2 veggies and 1 meat? And yes, I understand cheese is not a veggie, but for the sake of argument, just leave it in the list. All right. So looking at our veggie list, there are 6 different choices. We're choosing 2 of them. So 6 choose 2. There is 4 meats. We're going to choose 1 of them. And we're just going to take those 2 events and multiply those outcomes together. So we get 60 different omelets are possible with 2 veggies and 1 meet. Looking at example B, how many omelets can be ordered if we can afford at most 3 choices? Well, if you look at your two lists combined, there is 10 total toppings possible. If we want to choose at most 3, we have to consider the events with 3 choices, 2 choices, 1 choice, and 0 choices. Okay? At most 3 means 3, 2, 1, or 0. When you say the word or, instead of multiplying our outcomes together, we want to add, because keep in mind, these are different events. They're not happening simultaneously. You can't have a 3 topping omelet and a 2 topping omelet at the same time. Those are different events. They don't occur simultaneously, which is why we figure out those outcomes separately and then add them together. When you do add them together, you figure out there is 176 different omelet combinations with at most 3 choices. Okay? Looking at the last question, thinking about how many omelets can be ordered if you want at least 3. Well, you could take into account 3, 4, 5, 6, 7, 8, 9, 10. Or what we could do is look at 0, 1, and 2 and take that away from the whole. Okay, so we could use the complement. We can figure out these, since this is going to be less calculation, and subtract that from the whole. So the question is, we have these combinations. So we have a 0 topping omelet, a 1, and a 2, which we've already figured out. We want to subtract that from the total, and that should be what we're looking for, at least 3 outcomes. We don't care about these, so we're subtracting them from the total. So the question is, what is the total? Well, you can say yes or no to 10 different toppings. So if you think about this, green peppers, you can say yes or no. Red peppers, you can say yes or no. Onions, you can say yes or no. So with each of those 10 toppings, there's 2 outcomes possible. So we have 2 to the 10th is going to be the total number of ways in this sample space. We subtract off the ones we don't care about, and we wind up with 968 different combinations.